I'm Alex Halliday, Director of the Earth Institute. I'm pleased to welcome you to our reimagined open house for 2020. We're calling it Open House at Home. Every year we are excited to open up the campus at Lamont to the surrounding community to share our extraordinary research and our love of our amazing planet. This year, we are especially excited to host not just our local friends and colleagues, but also our virtual neighbors. So we're looking forward to lots of engagement with many of you around the issues of climate change tonight. So much has changed about the way we interact these days, and Lamont has had to think very, very creatively, as they typically do, about how to shift our in-person events and programming for Lamont Open House to an online format. These digital panels, education modules, lectures, demonstrations have allowed us to continue to meet with the core community where we live. And this is actually an amazing accomplishment. Just as the rest of the world is having to adapt to the COVID crisis, it's been great to see how we can do even something like an open house exhibition where people normally ramble around and mingle with each other in such an exciting and engaging way online this time. So Lamont's Open House is in many ways a celebration of science, and the science in particular that we do at Columbia University at the Lamont-Doherty Earth Observatory. And it's also a celebration of our extraordinary planet and how wonderful it is. It's a dynamic planet, and it's an exciting field of study, but it also, to some extent, is a planet that's under threat, and humanity is under threat, and the biosphere, and the way of life that we maybe become accustomed to. So we are facing challenges as we face a changing climate going forward. And we hope that we can ignite within you a deep and abiding love for the planet, but also a concern about its future going forward. Our many lectures offer an opportunity to hear directly from our scientists about their most current explorations and discoveries. And today's topic is carbon, and how we can remove it, or how we can control it, how we can decarbonize society. It's the single most important, carbon dioxide is the single most important greenhouse gas behind global warming. Global atmospheric carbon dioxide levels hit a new record high last year. Our climate research tells us that it is actually imperative that we remove these greenhouse gases and cut back the amounts on emissions. But all the scenarios for cutting emissions, even drastically, require us also to take carbon out of the atmosphere if we are to avoid hitting the critical temperature threshold of 1.5 degrees Celsius above pre-industrial levels, as required to avoid really dangerous global heating. So this is massively important. Carbon sequestration, pulling carbon from the air and storing it safely for the long term, must be a part of our global climate plan. There are several ways of going about that, and a lot of great research going on here at Columbia that we'd like to share with you. So today we are focusing on atmospheric carbon dioxide and what we can do about that. This evening, you'll hear from 3 experts, Lamont experts, who are looking at different aspects of this challenge. We have with us Galen McKinley, Roisin Commane, and Peter Kelemen. Galen, I'm going to ask each of them just to say a couple of sentences about how they got interested in this subject as I introduce them, okay? So this is going to be a flying start. Galen McKinley is Professor of Earth and Environmental Sciences at Columbia University and the Lamont-Doherty Earth Observatory. She is an ocean carbon cycle and climate scientist. Her research focuses on the physical, chemical, and ecological drivers of the global ocean's uptake of anthropogenic carbon. Galen, tell us how you got into this subject.
Yeah, thanks for having me. I started my scientific career as an engineer working in civil engineering. And then working in that area, I realized that the people in my office who were having the most fun were the people who were learning about the planet, who had PhDs in science. And I realized that that's really where I wanted to be, more than figuring out how to change things or build something for the use of humans. So that led me to do a PhD in climate and oceanography and to study the ocean carbon sink. And carbon sink is what I study because it is really the dominant control on the atmospheric CO2 concentration. And we need to understand the ocean sink because if the ocean sink changes in the future in ways we don't expect, it will rapidly dwarf any efforts we make to remove carbon from the atmosphere. So we really need to understand this critical sink, and that's what my research program is about.
Wow, fantastic, thank you. So Roisin Commane is an assistant professor in the Department of Earth and Environmental Sciences at the Lamont-Doherty Earth Observatory. Her research combines atmospheric science and biogeochemistry to examine questions about sources of trace gases in the atmosphere. Recently, she has started to build a network of measurement sites around the New York City area to monitor emissions of carbon and other pollutants. So Roisin, tell us about how you got interested in this subject.
Well, my background's in atmospheric chemistry, and I looked at a lot of pollution, and the largest source of many things are urban areas, and the CO2 emission from urban areas is just huge. So I've done a lot of like remote atmosphere work and measuring CO2 over the remote Pacific. And in 2016, we were measuring CO2 as part of a NASA program, and they had not that many months before had announced that CO2 passed 400 ppm at Mauna Loa. And then in the Southern Hemisphere, we were measuring 401.5 across the board. This was only 4 months later, and it just really shocked me. Maybe it was the jet lag, maybe it was we were on field campaign, exhaustion, but it really, really shocked me. So since then, I've been looking a lot more at, well, what is driving what we're seeing in the atmosphere? So when I moved to New York, I was very interested in learning more about New York because it's the largest urban CO2 source in the US. And figuring out what's driving that, the individual sources and sinks, and why is it making it such a large source of carbon dioxide, and what can we do about reducing that? So that's my interest in all of this.
Great, thanks, Roisin. And thirdly, we've got Peter Kelemen. Peter is the Arthur D. Storke Professor in Columbia University's Department of Earth and Environmental Sciences at Lamont-Doherty Earth Observatory. For the past dozen years, his research has included a focus on natural and engineered systems for CO2 removal from air and permanent geological storage via carbon mineralization during weathering and alteration of magnesium and calcium-rich rocks. Peter, tell us how you got into this field.
Thank you, Alex, for both things. But so I moved from Woods Hole Oceanographic Institution to Columbia in 2004. And when I arrived, I was lucky enough to meet and talk with people like Wally Broker and Klaus Lochner and Dave Goldberg, who had been thinking for quite a bit of time about how to use rocks to mitigate the greenhouse gas problem. And I jumped on board, trying to stay out of their way, and here I am. So I've kind of moved in the opposite direction from Galen. I started out as a very theoretical earth scientist, interested in reaction of magma moving through the interior of the earth. And now I spend a lot of my time talking to engineers.
Great, thanks, Peter. So I'm going to kick off with some questions. I'm going to ask each of the panelists some questions, ask them some questions together at the end, and then at the very end, we'll have some time for some questions from Q&A from people who are sort of listening in. But why don't I kick off with you, Galen? How great a role does our global ocean play in processing atmospheric carbon dioxide? From your introductory comments, it sounds pretty scary. We often hear Earth's forests are the lungs of our planet, but the oceans do quite a bit as well. Is that right?
Yeah, that's correct. So the ocean holds the vast majority of the carbon that's active in the current climate system, and the climate system that we inhabit and that we'll inhabit for the next hundreds of thousands of years. So when I say active, I mean not the rocks, because those take much longer to evolve. But the ocean holds about 36,000 petagrams of carbon, and the atmosphere only holds about 800, even with emissions in the recent centuries. So the ocean's holding about 45 times more carbon than the atmosphere. And that means that small changes in what the ocean is doing have the potential to strongly impact the atmosphere. Now, over the industrial era, humans have added about 400 petagrams of carbon to the atmosphere. But not all that carbon has stayed in the atmosphere. As I said before, only about 40%, only about 60% has stayed in the atmosphere, about 40% has gone into the ocean. So the ocean has been a sponge that's sopping up lots of our carbon and really reducing the amount of climate change that has occurred. So the ocean's providing this really critical climate regulation service. It's slowing down the rate of climate change. But of course, that doesn't come for free. Nothing comes for free, right? So the downside of the carbon going into the ocean is that the pH of the ocean is being reduced, and there's good evidence that that has negative effects on ocean biology. Because that means the ocean is becoming more acidic, and that's what we know and many people know as ocean acidification. So my focus is on this climate regulation service, regulation service provided by the ocean, but I just want to note that it's not all good. There is this downside.
So is the ocean's ability to sink carbon dioxide, which it's been doing forever, is that changing with a warming climate, and which way is that going, and how vital is it that we understand this impact?
So carbon is really very soluble in seawater, and that's why the ocean holds so much carbon compared to the atmosphere. And we're also adding so much carbon very rapidly to the atmosphere that we're essentially stuffing carbon into the ocean very quickly. And so the surface ocean holds a lot of our excess carbon. This excess carbon is mostly in the surface ocean because the ocean circulation is quite slow. It takes about 1,000 to 2,000 years for the ocean to overturn. So the vast majority of the carbon that we put in the atmosphere really remains stuck in the surface ocean. So there's sort of two pieces there. The carbon's soluble, but the ocean doesn't turn over very quickly. So that means that the future has some substantial uncertainties. And the most critical for the ocean sink is actually the amount of carbon that we choose to emit in the atmosphere. So in some work we've recently done, we show that if we continue to just put ever more carbon, exponentially increasing the carbon concentration in the atmosphere, for the next several decades, the ocean sink will pretty much continue to grow. And then it's only towards the end of the century when the chemistry of the surface ocean will change enough that we're going to cut down the ocean carbon sink to about 30% a 30% cut off what it would be if those chemistry changes didn't occur, is what I should say. However, unfortunately, things are not that much simpler if we do cut our emissions. If we cut our emissions, it turns out that the surface ocean is going to start to equilibrate with the atmosphere. This is Henry's law that we've learned in chemistry classes. And so if we really cut our emissions, the ocean sink is going to slow down very quickly as we cut our emissions, because there's all this excess carbon that's already stuck in the surface ocean, and the ocean hasn't had a chance to overturn. On long time scales of tens of thousands of years, about 85% of all of our emissions will go into the ocean. But in the meantime, in the next couple of decades, we have this situation where there's a strong interplay between what we emit and what goes into the ocean. And we need to be able to predict that quite accurately in order to be able to predict, how much could we actually emit in order to meet a temperature target, such as 1.5 or 2 degrees.
So just quickly following on from that, are you saying that you could actually end up with the ocean becoming more of a source than a sink?
Yeah, that's right. If we really cut our emissions down and we're starting to reduce the concentration in the atmosphere by our actions, because of this equilibration process, at least for some period of time, and it depends on how fast we bring down the atmosphere, there's going to be an equilibration. And that's just the natural reality of the world we live in, and the fact that we put so much carbon in the atmosphere. And of course, the further up we go, the further we put in the atmosphere, the more kind of reservoir of excess carbon is going to be in the surface ocean, and the longer that equilibration is going to take. So it really behooves us to start soon on our cuts.
Okay. So you're one last question. You're embarking on a 3-year project with NOAA. Unless I've got this wrong, it sounds like you're using modern data science techniques to make monthly mapped estimates of the amount of carbon dioxide in seawater. So why is this level of analysis important? And maybe you can say something in layperson's terms about what the data science techniques are and why they're so important. But also, why is it important for the future of the planet in particular?
Yeah, so how do we know what the ocean carbon fluxes are and how they're changing in time? The best way to know that is from data. And so actually starting in the 1950s at Lamont-Doherty, who we just lost in the last year from the Lamont community, he figured out how we could observe surface ocean carbon directly and do it autonomously actually on ships that are crossing the global ocean. And so now in the database that he started, there are 25 million observations in that database going back to about the 1980s. And so that's a lot of data, which is amazing, but still the ocean is extremely undersampled. In fact, of all the potential 100 by 100 kilometer spots that you might observe every month for the last decades, we've only observed about 2% of the global ocean. And from that, we want to understand how the ocean carbon sink is changing, how, for example, it's responding to changes in the atmospheric CO2 growth rate, as I mentioned before. And to do that, that's been a challenge. And modern data science that's really just coming along now, changing all industry and commerce, right? Neural networks and artificial intelligence. It's really made a lot of progress in our ability to make those extrapolations and to assess their quality. And so the goal is that we can really understand in this project that we're doing with NOAA, make better extrapolations, better understand the uncertainty in those extrapolations, and also plan new observational programs that can sort of fill in the gaps, essentially, where we don't have information. And on the long term, hoping that this can become part of a monitoring system where we can really quantify how much carbon is going in the ocean very accurately and help everyone understand that if we are cutting our emissions, the ocean is giving us this much back. And the more we can really say why things are happening, the more we can keep on track with the mitigation efforts.
Okay. That's great. So, Roisin, maybe I could move to you now and just ask you some questions. Could you tell us about, there was this great article, I guess it was in the New York Times, was it, where reported about New York emissions and how they were changing. Can you tell us about your recent work and in terms of how the pandemic-related shutdown has diminished carbon dioxide?
Sure. So a lot of the focus from, say, the media was on the air quality itself. So things like carbon monoxide, NO2, so things that you could automatically, you could feel straight away whether or not you were breathing in some of these things. And what we found, so we've been measuring in Harlem at a site at City University of New York, and we were really interested to see how much of a difference we would see given there was a 60% drop in traffic in New York City. And we saw the CO levels dropped about 40%, but the CO only dropped maybe 10%. Now, if we actually understood what the sources of CO2 in New York City were, we would have very different responses from that. By what I mean is, a lot of cities come up with an inventory. So they do it accounting tricks to explain, what they're seeing for, we expect to see X amount from this process. We expect to see Y amount from another. So in New York City, it's estimated that about a third of the CO2 emissions are from traffic, from transportation. Another third are from energy and building use. So electricity, there's 24 power plants within New York City limits. And then if we have the amount of CO2 coming from that, that's often the reason that New York is such a big source of CO2. It's the fourth largest mega city source of CO2 in the world, which is quite surprising for a city, say in the US. You would expect there'd be a lot of development. It's a very old city. The infrastructure is quite old. So we had a large drop in traffic and yet only a 5 or 10% drop in the CO2. Now, what we measure in the atmosphere is oftentimes a mixture of what the weather tells us and the emission changes. So as the weather changes, the boundary layer goes up and down. We also have to account for that. So oftentimes there's been a lot of studies that have been published on COVID effects. And about half of those studies, I think there was something like 200 odd papers have been published on the air quality up to the end of September. And yet half of those never even took weather into account. which is how much a concentration is in the atmosphere, is dependent on how high the boundary layer is, what the weather is doing, and how much you're emitting at the bottom. So they were attributing all these changes to emissions, but that was not what was going on. So we've been finding that actually the changes in emissions for CO2 in New York have been much less than we would expect if the traffic was really accounting for a third of the total CO2 emissions for the city. So what does that mean for where are all these emissions coming from? So we've been working with John Mack at Stony Brook University and other people within New York City to try and understand the other chemistry that's happening. So if you have a lot from diesel, you will see a lot of benzene, toluene, other air toxics. Or if you're seeing a lot of petrol cars, you'll see a lot more NO2, and we saw a pretty big drop in that. So most of the traffic drop was in light vehicles, so traffic cars, and yet we didn't see a large drop in heavy duty diesel vehicles. And yet we also did not see much of a drop in population, except on the Upper West Side. So we're also measuring methane, and what we saw a surprisingly large drop in methane, which is also one of the greenhouse gases that we can really get something from if we reduce those emissions soon, because the lifetime is so much shorter than CO2. So there's a big focus in New York City on reducing methane. We saw a surprisingly large drop in methane. As far as we can tell, it was related to the sewage treatment plants. So the population on the Upper West Side and Midtown Manhattan plummeted, yet not everybody left. So it doesn't quite follow. We're still trying to figure out some of the sources of methane, but that was a surprisingly large impact, was population changes around New York City. So for methane in New York City, it's about 3 times higher than the EPA thinks it should be. And everybody has just assumed it must be the natural gas network. And the observations we have are saying that, no, it's not just the natural gas network leaking. There's other stuff going on. So having ways to measure what we think should be happening. So measuring in the atmosphere, we can tell if what we think is happening on the ground is actually real. And that's one of the big strengths for that. We can help the governments of various cities and states figure out what they should be targeting. What are the processes that will give them the most impact for reducing emissions based on what we're seeing in the atmosphere? So that's a lot of what I've been looking on. So I think COVID was a wonderful experiment in how to figure out, okay, we take all the cars off the road and turn the entire fleet electric. We won't see half as much of a CO2 improvement as we thought we should, because we're not concentrating on the right things. So that's kind of the focus that came from that. So that's been very interesting for discussions.
So you were very surprised by these results, I guess.
I was surprised at how fast the CO2, how small that CO2 change was. I thought we'd see a massive change. We saw a big change in CO, we saw a big change in other pollutants, but we didn't, sorry for the cat. We did not see as much of a change as I would have expected if we understood the sources around New York City.
Right. You've also been researching carbon dioxide that gets absorbed by plants, I understand, and on land and released from soils in the Arctic. So can you tell me what you're doing in that area, and tell us also how this is linked to climate change?
Well, I've done a lot of work in the Arctic, looking at CO2 uptake by vegetation and then release from microbes in the soils. But what became really obvious was it's warming so quickly in the Arctic, and that's not their fault. So it's become a kind of a topic of discussion among Arctic researchers. We're looking at the repercussions of climate change. We're just cataloging what's happening, and can be quite depressing. So it's not getting cold in the winter. So it's not that it's not getting cold, it's not getting as cold as it used to. So soils are not completely freezing through. Permafrost is thawing, buildings are collapsing, villages are having to move. And a lot of the microbes in the soils are still staying very active very late into the winter. So at some of the sites that my colleagues are running, sites that should be freezing, they're as far north as you can get, and they often are not freezing through now. So they see CO2 production way later than they should, and they see methane never stop coming out of the soils. Now that's kind of a feedback loop that there's not much we can do about that if that really becomes a runaway process. But all of it is driven by the temperatures based on the huge emissions that we have in like the mid latitude, so down where people live. So the current fluxes are tiny compared to what I'm measuring in New York City, but the implications are massive. So the Arctic stores about twice as much carbon as is in the atmosphere right now. It's really old frozen peatlands. And that carbon is just waiting to be chomped by various microbes. So you hear about reindeer mass graves, and they're beginning to thaw out again, and anthrax is spreading. So when you think about microbes like that really should be frozen, and they're starting to thaw, it begins to have a very large effect around places. Now, in certain areas, it means that vegetation will grow that much better because it's warmer, but because it's so far north, it runs out of daylight. So you end up with springtime can start to come earlier because it's warmer, but the fall, they run out of daylight and the soils take over from what the vegetation could do. And that feedback loop starts to become a really big problem. Now, for biogenic stuff, we actually see a big effect of that in New York City even. We've been measuring how much the CO2 drops over the summer. And in some cities like Boston, it's been measured, and I think we were seeing it here this summer as well. Most of the emissions, so in Boston, all of the afternoon CO2 emissions from people in the city are taken up by the trees in the city. But the problem is trees take up CO2 during the day. They give most of it, except for a tiny bit they used to grow, back out again at night. So those trees, while they're a reservoir of carbon, they're very susceptible to dying very quickly in urban areas. And you have wildfires like California and Australia, and all that carbon just goes straight back into the atmosphere. So while planting trees is wonderful, it's very temporary as a way to take carbon out of the atmosphere.
Mm.
But it makes for very interesting atmospheric chemistry when we're trying to measure all of it.
Right. So that segues nicely to talking to Peter Kelemen. Peter, tell us about carbon capture. We've talked about the oceans, we've talked about the atmosphere, and now we're talking about how to get the stuff back into rocks. You're the world expert in this. Can you tell us what carbon capture is and how does it work?
So when we talk about carbon capture, we're talking about removing greenhouse gases, typically CO2, from human emission sources and directly from the air. And I'll kind of skip over the emission sources. So even in models that assume that we're going to generate all our electricity from renewable energy or capture all the greenhouse gases from all the smokestacks, the IPCC and other experts have discovered over the past few years that we will still need to remove CO2 directly from the air. And that's quite hard to do, right? So smokestack gas can be 10 or 100% CO2, but the air is 100 times lower concentration. And so it's a challenging thing to do, but it's something that apparently will be necessary to hold warming less than 2 degrees C. Experts estimate that we have to remove 10 billion tons of CO2 from air per year by mid-century. And just to put that in context, that's about twice as much CO2 as we produce oil and gas on the surface of the planet every year. So it's a lot of fluid. And the simplest methods to do this involve liquid solvents or sorbents that take CO2 from gas. But what we've kind of recently discovered is that we should stop focusing on fancy things and just use very simple chemical reactions to take CO2 from air because it's cheaper.
So, so that sounds amazing. So, is the technology for this developed already and enough to help society actually mitigate climate change?
Yeah, it's really pretty straightforward stuff, actually. Certainly not rocket science. And so if someone wanted to scale up, we could do 10 billion tons a year right now. Obviously, there's lots of ongoing research, and I'm really heavily involved in that. But that's all about kind of optimizing on the margins, trying to make it cheaper and quicker. But we could do it for something like 2% of global GDP or 3% of global GDP. And just for reference, that's about how much we spend on sewage treatment and waste management every year. So it's not a lot of money. The other thing to keep in mind is that people tend to view this as a cost. Like somehow we're burdening the economy with the cost of this process. But of course, the money goes somewhere. We pay people to do this. And so it's actually not evident to me that it's actually an economic net loss.
Right, right. So, so this sounds like, I don't want to make it sound, I mean, actually rocket science is not very difficult. So if you're making it easier than rocket science, then this should be a no-brainer. So what are the major obstacles to making carbon capture a reality? Presumably it's
Obviously, I mean, again, we're beavering away, trying to make it cheaper all the time. But the main issue is that no one's paying.
Yeah.
So it's really hard for one nation to unilaterally do this. Because the CO2 in the air is well mixed, and reducing CO2 emissions or taking CO2 out of the air here affects everyone equally. So there's an issue. There's not a global consensus around paying for this. And so, we are working to prepare for the day when people are ready to pay for this. And I like to say, again, the costs are comparable to sewage treatment. So when people think that putting CO2 in the air is similar to throwing poop in the street, we're all set. We'll do it.
Okay. So that's great. So, so your own work around this has been very much, I just want to quickly, just before drifting off you, Peter, your own work has been very much around finding natural solutions for doing this.
Yeah, so there are rocks on the planet that are really, really far from equilibrium with the atmosphere and surface waters, including the ocean. And so they react pretty readily with the air to form solid carbonate minerals. And they take CO2 from air and make these minerals. They're inert, they're non-toxic on a human time scale that basically store CO2 permanently. And so we've been trying to, first of all, alert the scientific community to the fact that this kind of chemical potential energy just exists, is lying around for use. And if one could find ways to speed up this natural weathering and CO2 uptake, it could be quite a bit cheaper than more highly engineered methods. And in a way, we're kind of pushing back. It's easy for engineers to come up with fairly complicated processes, and we keep sort of pulling back and saying, look, why don't we do this dumb thing? We know how much that will cost. We don't have to estimate what future technology improvement might bring. We can use present day techniques with known costs to do this at potentially a lower cost than these more complicated processes.
Wow, so that's amazing.
I don't know if I'm answering your question, Alex, but that's.
Well, I was just trying to understand whether your way of doing it involving reaction with rocks is actually just an alternative to artificial trees and things like that have been considered, or whether you need a bit of both, or how you view that.
I would never, it's really important in this business for nobody to extend their elbows. No one has a silver bullet. It's been well established for a long time that no single technique is going to, by itself, mitigate the greenhouse gas problem. And so we need lots of things going together in parallel. Right now, the method that we're most excited about is less expensive. Don't listen to reporters, but in sort of peer-reviewed scientific literature, it's the lowest estimated cost of any method for taking CO2 from air.
Okay, so can I just, in the last few minutes, I wanted to ask, before we open this up to the audience, I just wanted to ask some questions of all of you, which you can just dive in and feel free to go crazy and interrupt and all that stuff. So first of all, the Paris Climate Accord. So what are your views on this? Because the current US administration has stated its intention to withdraw, and that's now imminent. It's going to be fairly soon. What would you hope to see happen if actually that happened? And, despite that intention, what would you want to see happen? Yeah, Peter.
Well, so I actually teach a class on Earth resources, and today I was showing some information about, for example, CO2 emissions in India, which are rising pretty fast, might be 8% per year. And one of the students who's from India jumped in, and we were talking about this. And, India is a signatory to the Paris Accords, and to a certain extent, India doesn't care that much what the US does, and certainly doesn't need help from the US. So what's going to happen? And the good news would be if solar generation of electricity became more inexpensive than using coal. And it very likely could happen, because in small rural villages that are far away from power plants, you can put up solar panels right there, and you don't have to worry about the transmission network. So there's lots of good things that can happen that don't really matter too much what the US administration does. And so there's reason for optimism, but we sure have a long way to go.
So Galen, do you want to come in?
Yeah, I just want to remind everybody that, this is it's a global problem. And so the emissions in other countries really do matter. And I just think it's a sad lack of leadership of the United States to not stand up for a responsibility in this problem, and to push the burden of climate change off onto people who are less capable of not developed so much to the current point, not of that opportunity, and are going to suffer the consequences. But if the people of the world step up, and China, for example, meets its commitments that it's making ever increasingly now, we can have a strong impact on climate change without the United States. And I really hope that the people of the world will. I think in the end, the US is going to be behind, because we're going to not have the technologies to do all the things that you need to do to decarbonize as much as the rest of the world. So I think it's a bad choice. But I have hope that the rest of the world can lead if we choose not to.
So just let me get Roisin.
Just a quick thing. So I think in the US, the states are taking the lead.
Mhm.
So I know New York and California, those economies are massive enough that they can actually take the lead across the US. So New York City, Chicago, and LA are the three largest sources of CO2 outside of power plants. So as long as each state starts taking it seriously, I think the US can end up doing a huge amount towards the Paris Agreement without the federal government ever saying anything. And that has me still quite hopeful about things, because
Okay.
California and New York are doing a huge amount.
Okay. Peter, you wanted to come in quickly on that?
Yeah, so I think that until recently, the global community expected the US to lead in this, both because of the US has so many resources, and also because we remain by far the highest emitter per capita and the largest emitter over time. And so I didn't mean to minimize that. So it's very unfortunate, in my view, that the US has chosen not to lead. And we can hope that that will change.
Okay. So I'm going to quickly, we're going to go over to the audience in a minute, but I just wanted to finish by asking each of you, one last thing that you would like to take home message, if you like, for the audience about carbon and our future. What would you like the public to know? Let's start with you, Galen.
Yeah, I think one of the really important things for people to know is that the mitigation that we embark on now, it really isn't going to change very much the climate that we experience in our lifetimes. And so we're really talking about changing now in order to improve the lives of our children and our grandchildren. And we invest so much in our children and our grandchildren. And I think this is something we just need to do in order to leave the planet in a place where they can take advantage of all the things that we've built up, all the infrastructure that we've created and our parents and grandparents have created, like we hope they can. But we're gonna also have to adapt, and we should not lose hope in our efforts of mitigation at the same time that we're adapting to some significant changes that are gonna occur.
Okay. Roisin?
So I think all anthropogenic carbon emissions are tied in with air quality issues. So every CO2 source is a source of air pollution, and 9 million people died last year from bad air quality. So if we're going to ask for changes in our carbon emissions, we need to start asking politicians to make sure that that is happening and that it benefits us as good air quality. It would be one of the best things we could possibly do, because it would have an immediate health effect, and yet then we would have the long-term impact of changing climate. And I think having that discussion at the same time is really important. In Europe, they brought in laws to encourage diesel because it was more technically more climate, it was a climate benefit. and their air quality has just gone downhill for the last 20 years. And so I think any carbon reduction strategy we have, we need to keep the co-benefits in mind. Financially, reducing carbon, given what you could do to air quality, it is a no-brainer. We could vastly improve air quality and economic outputs at the same time as reducing carbon if we had the political push to do that. And I think people are beginning to get to that stage now. I think it's quite important to make sure everybody realizes every CO2 source is a source of something else you don't want to breathe.
Yeah, that's a really good point. Peter, give us your final take-home message for the audience.
Okay, well, I think rather than, first of all, I will speak for myself, but rather than using my own words, I'm going to read to you from an op-ed that appeared earlier this week in the New York Times by Margaret Reinke. And I emphasize, right, this is not Columbia University's point of view. This is my point of view. Every single issue that matters to me, Margaret wrote, education, social justice, women's rights, affordable health care, criminal justice reform, gun control, immigration policy, won't mean a single thing if the planet becomes uninhabitable. The same is true for my brothers and sisters across the political aisle. They care about the right to life. If they care about the right to life, as they say they do, if they care about the economy, about freedom, about national security, as they say they do, then they have no choice in this election but to vote for candidates who are committed to halting the rate at which the planet is heating up. For now and for the foreseeable future, there is only one issue, and in this election, there is only one choice, because there is only one planet we can call home.
That's great. Very good point. I have to say, one of the great things that we've enjoyed doing here at Columbia is not only thinking about the sustainability of the planet in our science, but also in terms of the way we actually think about the sustainability of our campus. And Lamont has been amazing in this respect. It's moved heavily towards sustainable energy in terms of how to provide its own energy requirements, which are considerable. But there's also another aspect to what we do at Columbia, and that is to engage with policymakers. And I think one of the things that's been great is to see increasing engagement of our science with people in government in a bipartisan way, which I think is really, when you talk to people privately, you know, a lot of politicians on both sides of the aisle actually do get it, and they realize how important this is. So there are major opportunities, I think, for us going forward. I want to switch to the audience now, so and get some questions that have come in. So I'm going to kick off with the question, which is, I guess, really for you in the first instance, Galen. Since sea levels are rising, at least in part due to melting of ice fields and glaciers, this means a large inflow of fresh water. Will this affect carbon uptake in the oceans? And what are the other effects?
Right, so the main way melting glaciers have the potential to affect the ocean carbon sink is if those melting events happen very rapidly in the high latitudes and therefore modify the overturning circulation of the ocean. So one of the main ways the ocean carbon sink is sustained, it really is sustained because we continue, the ocean, although slowly, does overturn and brings up waters from depth that are not already laden with our anthropogenic carbon, and in return our anthropogenic carbon laden waters end up in the deep ocean. But particularly in the North Atlantic, if we flood the North Atlantic with lots of fresh water from Greenland, it's quite possible that that circulation will slow down or potentially stop, and that would certainly slow down the rate of carbon uptake by the ocean.
Okay, and I think this one's for you, Roisin, although Galen may also have some points. There's also an issue here about increasing, can regenerative agriculture play a part in CO2 sequestration by increasing the microbial content of soils and drawing down carbon from enhanced plant growth? How about planting trees? I think Peter can come in on this as well. But Roisin, what do you think of planting trees to get CO2 out of the atmosphere?
I think it depends where you're talking about planting them. So I'm Irish, and there's been a big back in when I was a kid, there was a big program about planting trees in some of the peat bogs. And all it did was strip the carbon out and end up with more CO2 going into the atmosphere. So draining the peat bogs meant methane and CO2 was released, and those trees never thrived. They all died off eventually anyway. So I think it does very much depend what you mean by planting trees. Keeping the ones we already have alive would be a much better way of keeping carbon in the ground and in the biosphere. So when we have a lot of wildfires like we've had this year, we can plant trees, but if we're not looking after them, and if given everything else that's happening, it doesn't mean that it's a permanent reservoir of CO2. You can often, like, they have a cycle, they have a lifetime. And it's in cities, for example, trees don't last anything like as long as they do in a forest. They've got a lot more water availability and sewage. They tap into the sewage lines. They grow much, much faster. So they take up more carbon, but then they only live half as long. The stress of all the pollution and everything else means that they just die a lot quicker. They're stripped out and then they decompose and all that carbon goes back into the atmosphere. So I think we kind of need to be careful what we mean by planting trees is great. Making sure they are thriving is what I would nearly focus on, more so than just planting trees and abandoning them.
So thanks, Roisin. Peter, you co-authored the National Academy's report on carbon removal from the atmosphere, and tell us about trees and
you're way ahead of me, Alex. That's great. So I was very fortunate to sit on this committee that looked at so-called negative emissions technology for removing CO2 from air. And that committee was led by Steve Bacala, who's a professor at Princeton, and a real booster for increasing soil carbon. So I learned quite a bit. And basically, to make it simple, industrial agriculture, basically because of tilling and removal of waste material, strips carbon from soil. And that's very widespread. So if soil carbon were restored to its original levels, that would take up about 20 years of human emissions at present day rates. It's completely not trivial, and it's quite inexpensive. And there are data. Steve used to show these plots, they look terrible, but he said, look, all the values are positive. There are data that suggests that the higher the soil carbon, the more productivity you get per acre of land. So that's a win-win. And then the question is, then why isn't this widely adopted? No-till and things like that, no-till agriculture, what the inquiry is calling regenerative agriculture. Why isn't it more widely adopted? And academics often drift off into discussions about how farmers aren't very smart, which is totally obviously wrong. So I think what's needed maybe is so-called patient capital. A lot of farmers are deeply in debt. They can't change practices that might reduce their year-to-year productivity for a few years. I think if anyone was serious about promoting soil carbon regeneration, then just loans that didn't start to come due for a few years would make a big difference.
Well, that's a really interesting point.
And it's a big sink. I mean, we sort of thought that might be the biggest and most achievable. And as we look at this 10 billion tons by mid-century that we need to remove from air, that's maybe the easy piece.
Yeah, and there's some big chunks of stuff to be sorted out still: manufacturing, land use, etc.
Well, and there's just billions of farmers who have individual jurisdiction over what happens on their land, and so it's a lot of people to persuade.
Yeah. So there's another question here about there's a lot of interest in the oceans here. So Galen, get ready. So we hear there's increasing carbon in the air and therefore in the oceans. Should we both look at pulling carbon from both?
I have not heard a lot about the idea of removing carbon from the ocean. Our focus really has been about removing it from the atmosphere. For example, adding alkalinity to the ocean, which would allow greater uptake of carbon into the ocean, is one idea that has been considered for carbon dioxide removal. People have suggested, for example, enhancing the biological pump in the ocean to remove more carbon to the deep ocean by adding iron to the ocean, but that's logistically incredibly infeasible, and we don't even know if it could work. So yeah, I don't really think that removing it from the ocean directly is something that is being considered. It seems feasible.
Okay, so we got a follow-up question. So this is regarding the issue of CO2 emissions reduction affecting the performance of the ocean, the carbon sink. So what needs to be done? So this is, you're right at the front end of this, Galen, because I know about your recent work here at Columbia. But what needs to be done to create more holistic modeling of climate change to capture all of the system effects, including the thawing of the permafrost?
Yeah, so
on this, right?
yeah, right. So we do have climate models that represent the carbon cycle, but the challenge in the whole carbon cycle as a whole is the great heterogeneity in the climate system. So on the land, we have permafrost here, we have a lake here, for example, we have a forest there. How do you represent all of that in a computer and not get so complicated that you can't afford to run the simulation? So we always have a challenge that we can't resolve all the processes we want to, nor do we understand them well enough to represent them. For the ocean carbon component, which I know best, the basic processes of the fact that the ocean sink is responding to atmospheric growth rate of CO2, and that if that growth rate slows down, we're going to have a reduced sink. That is in the models to first order. But what we don't have as good in the models as we need to is, for example, the physical oceanography of the ocean. How is the ocean structured? How rapidly is it overturning? How quickly are the perturbations at the surface really making it to depth? We have a lot more work that we need to do to better represent the small scale processes, particularly in the physics of the ocean. And so we have opportunities to do that, again, by harnessing data science techniques. That's something that we're trying to work on, and to build better representations of how the ocean works in detail. And that will reduce our uncertainty in our projections about the future ocean carbon sink under various emission scenarios. And the other thing I'll say is that most of the studies to date have really focused on high emission scenarios. So it's also a situation where we just haven't looked at it very much, in part because everyone's been focused on this idea that business as usual, high emissions, we're not going to mitigate. And I think our community is just beginning to realize that we need to take a deeper look at understanding what the uncertainties are with respect to lower emission scenarios, or scenarios where we're taking a lot of carbon out of the atmosphere by human activities, by human interventions.
Okay, so Roisin, just a quick follow-up on that. I was going to ask you, because you've been working on permafrost stuff, are you sort of, how dangerous is the situation there from the point of view of, I mean, it's fine to have the models, but do we actually understand the basic system well enough to be able to, with confidence, predict the future? Or could things get much worse than we've been thinking?
So I don't think anybody thinks all of the carbon in the Arctic is going to end up in the atmosphere in the next 10 years kind of thing. Most of the climate models, most of the large models, CESM type thing, they had predicted that permafrost would begin to thaw by 2100. The problem is we're seeing it now. So it was a process that just, they thought it was going to happen, but just way later in the future. So they're having to kind of dial it back into, okay, well, this is happening slowly. I mean, we're just seeing the start of this happening. And it's mainly because so in the Arctic, as things freeze up, you get what's called a zero curtain. So there's a layer of permafrost, and then you get a layer that thaws on top of that in the summer. And then that freezes through in the winter. Now, up until 2012, I think was about the first time we saw it, that would freeze through in about 2 weeks. And then in the last 2012, 13, 14, 15, that's now taking 3 months. This is a process we knew could happen, but we had no appreciation of the fact that it's now a quarter of our annual cycle in the Arctic. Now, we thought it would eventually happen. We just had no concept of when that would happen. Right. So I think it's more about the potential of what else we could be missing, rather than there's only a certain amount of carbon there that will be released. And I think the numbers are still much, much smaller than anything we're emitting down here, for example, but it's the potential for it. And what else have we missed? That's the kind of what the main focus is lately.
I mean, that is one of the amazing things about climate change, is that we're actually discovering, as the climate changes, how the climate works at some level. And so there are new phenomena that are being discovered, which is really interesting science, but actually quite scary, because you think, well, what do we not know yet? You know,
And there are quite a few studies that have been doing, warming experiments. So they warm the soil to see what will the impact be as it's getting warmer. The problem is their controls are no longer cool enough to be able to use as a control. So that like everything is warming so quickly that like, how do you control for the fact that it is warming so quickly? So it's become very difficult to fully get a handle on what we think might change other than everything. So that's been, yeah.
Right. One last quick question for Peter, and then there's gonna be a final question I want to give to each of you, which is, what advice would you give to a young scientist interested in carbon and carbon sequestration? So you can think about that. And meanwhile, I'm going to ask Peter about one question here. Are there ways to recycle carbon for use in new products? And would that be a useful strategy?
There are. The thing that people tend to focus on is trying to use carbon in cement and concrete, because we make so many billion tons of cement and concrete every year. And so if you could incorporate CO2 into that product, it would make a big difference. That's still a viable thing, but most of the technologies that have emerged are not going to be huge sinks for CO2. I'm kind of a skeptic a little bit that the market for CO2 could ever reach billions of tons. There are, of course, many uses for carbon, but I don't think we're going to see carbon fiber buildings and carbon fiber airplanes in a time scale that will be useful to the greenhouse gas mitigation effort that we need to see in the next 50 years.
Okay. Well, that's an interesting point for discussion, certainly. So going forward. Okay, just to wrap up, we've got 3 minutes left, so it's 1 minute each. Galen, what advice would you give to a young scientist interested in carbon and carbon sequestration?
So I would say, carbon is everywhere, and the solution to carbon is everywhere, really. So whether you're interested in mechanical engineering or civil engineering, whether you're interested in doing the natural science, whether you're interested in computer science or physics, there's so many ways in which we can all put our intelligence and efforts into addressing the issue of carbon. So it's all there.
Great. Roisin, what about you?
I guess something that became evident during COVID to me was that a lot of what we push as personal responsibility on people, it really doesn't make that much of a difference. I was very disillusioned. But what it does mean is that if we really want to change something, we're going to have to start pushing politically. Whatever way you want to take that is up to you. But ignoring the fact that politics is going to control how much carbon's in the atmosphere is not really an option anymore. So learn as much as you can. Be the science voice in that discussion. That would be my advice to people going forward. We need more informed scientific input in the political discussion, and that's going to be on the next generation, who are much better equipped at that than the likes of me.
Great. Peter, what about you?
Well, suppose you want a job. And so then, yes, the policy sphere is super important. It's more important than what I do. The business of taking CO2 out of the air is going to accommodate some jobs, but probably not that many. All these people want to do internships with me. I love you, but there's only so many spots. So the big growth is going to be in the energy transition, is going to be converting, in particular, electric generation from fossil fuels to renewables and perhaps nuclear. And in addition, going with that, because of the intermittent nature of renewable energy generation, is going to be energy storage. So, when The Graduate, somebody tells the Dustin Hoffman character plastics, I would say the comparable thing in this time is energy storage.
Forgotten the Dustin Hoffman Graduate thing. Okay, great. Well, thank you very much to Galen, Roisin, and Peter for your amazing answers, and very, very interesting, amazing science. And this tells you a little bit, so it's a tiny snippet. I mean, I've got to be rude to these people. They're brilliant, but they're just a fraction of the brilliance that there is at Lamont. And so there are many more people there that you can get to know through engaging. Please take a look at the Lamont website. There's plenty more information on there. keep looking at open house. We're very interested in K-12 learning experiences, and there's lots of great stuff there for you. And also, please support our work by making a gift. This is really important. Lamont is a really, really important place in terms of the future of our planet. And we need your support to make sure that we can carry on doing this amazing work going forward. So thank you again, and thank you to the audience, and thanks for the questions, and thanks to our panelists, and look forward to keeping in touch. Bye-bye for now.